So it's always hard to know coming into a group that's been together for a while what they know and what they don't. And so you have to help me with that, especially if I say things you don't know or things you'd like to know better. Don't hesitate to raise your hand and ask. You'll probably do everybody around you a great favor because they don't know either and they're just pretending, but they're not brave enough to say so. So that said, I want to talk about free resolutions and some stuff that's been going on there lately. And there is a connection with cones and fans, although it was never obvious to me that that would be the case before. Let me start with a little bit of notation, just to get everybody on the same page. So I'm always going to work over a polynomial ring, S, in n variables. And I'm always going to think about graded modules, so I'll think of the ring as graded, with the degrees of the generators all 1, nothing fancy. In fact, you'll see that one of the things I don't know how to do is to extend this in the obvious case of toric geometry, where there's another grading and maybe another irrelevant ideal. All the machinery is there to state something, except I don't know what to state. And I certainly don't know how to prove it. So that's perhaps for you to think about. Anyway, we'll come back to that. And then I'm interested in invariance of finitely generated graded modules. So I better have a finitely generated graded module. And of course, the main way of getting a numerical invariant is to look at the Hilbert function. So you could take the dimension of the dth graded component of M for each d, and then you prove, easy proof, large D, that's a polynomial function of D, and so you have coefficients. And even for small d, it's an interesting function, and you can try to analyze that. So you can look at the Hilbert function. Hilbert's original motivation for that was to look at a very classical problem. He was interested in the case where you have a polynomial ring like this and a finite group acting on it, or maybe a big group, a Lie group like SLN or GLN, and you look at the ring of invariance. That's a graded something. It's a graded ring anyway. And in many cases, it's a finitely generated graded ring. So you could look at it as a module over some other polynomial ring, maybe in the number of generators, and then ask about its Hilbert function. That would compute the number of invariants of each degree. And that was a classical problem that occupied most of algebra in the late 19th century. I think that's no exaggeration. And there were dozens and dozens of papers analyzing very, very special cases and proving in those special cases that that was a polynomial function, or turns out to be a kind of rational generating function is what you want to prove in that situation where the degrees of the generators can be different. And Hilbert then proved in great generality this theorem that I just said about Hilbert functions and sort of ended the field for 50 years while people recovered from this blow and figured out what question to ask next. And this was a very controversial business because he didn't actually compute any invariance, which is the way it had been done before. So this is a kind of important thing in the history of mathematics, not only in our subject. Now, the way Hilbert proved his theorem, not the way it's usually proved in modern texts, was to say that M can be compared to free modules. And the mechanism for doing that he introduced, it had been around before. Cayley had thought about these things too in the middle of the 19th century, but Hilbert put this all on a better footing, was to look at a free resolution. So you take M and you say, well, it would be nice if it were free. Free means finitely many generators, independent. Then I could compute the Hilbert function just from knowing the Hilbert function of S, because the Hilbert function of S is just given by some binomial coefficient, which you've all seen, of course. Well, okay, maybe it's not free. So then we should compare it with a free module by mapping a free module onto it. And since we want to keep track of degrees, we better keep track of the generators of degrees. So if you have generators of degree di, then you could let's say, beta I of them, then you could take here a free module with generator in degree di and raise it to the power corresponding to the number of generators. Let me, in anticipation of what's coming, call that beta 0 di. So let me get rid of the di and just say j beta 0 j. And does everybody know this notation? This is the free module with one generator in degree plus j. I apologize for that, but it's been forced on us by Grothendieck and others and makes a certain sense. The way to think about that is that if you take m and put an of j in front of it, or of minus j, then the degree d part of that is m in degree d minus j. You just add whatever's in the bracket. So from that point of view, it's very natural. If you look at degrees of generators, it looks funny. Anyway, so that's the first step. And now, if you have a surjection like that, let's say it was a surjection, then at least you know that the Hilbert function of this, which you can compute just by adding up Hilbert functions of S, is bigger than or equal to that. And unfortunately, probably not equal if m isn't free. The difference is in the kernel. So you could say, well, I wish I knew the Hilbert function of the kernel. And Hilbert says, well, just do this again. That seems like very bad advice at first, but it comes from Hilbert, so we might as well follow it. S of minus j to the beta 1j. And now, again, we can say something about the Hilbert function of the kernel, but unfortunately, there's the kernel left. So you think, well, I'm going to chase my tail forever. But Hilbert proved in that first big paper that this process stops after finitely many steps. And you can put a 0 back here. And so you can really compute the Hilbert function of m, not just the Hilbert polynomial, as an alternating sum of Hilbert functions of free modules. So that's the original Hilbert function idea. Now, there's actually a much finer invariant hiding there, which I think you heard about last night, probably knew about before anyway, which is these beta ij's themselves. So this I'll call the Betti table of m. And of course, to make it an invariant, I'd need to have something unique. Free resolutions, as I've stated it, are not unique. But if at every stage I chose the minimal number of generators required, the minimal number of generators of m, the minimal number of generators of the kernel, then it's a pretty easy theorem, comes from Nakayama's lemma, that the answer I get is unique up to isomorphism, up to non-unique isomorphism, unfortunately. And that's why the derived category exists, to fix that problem. But we don't have to go there, and I don't intend to. So if I take a minimal free resolution, then it is unique. And that fact means that what I could call beta ij of m is an invariant of m. I'd like to think of them all at once for this moment. And so I'll think of this as a set of invariants, really. Put some brackets around it. Most of them are 0. There are only finitely many beta ij's that are not 0. But potentially there are a lot of them, right? What vector space do they live in? This invariant sits inside the direct sum from minus infinity to infinity. That's the j of, let's say, z or n to the, well, how many terms would there be? You start with the 0th term, and the last term will be the nth term, so there'll be n plus 1 terms. So it's a sum of z to the n plus 1s. But for reasons that are going to become apparent in a minute, I'm going to put q here instead to the n plus 1. So I'll think of that as an element of this infinite dimensional vector space. Okay? One gets uncomfortable when one sees an infinite dimensional vector space, but this is a pretty harmless one, and all our elements only have finitely many non-zero terms anyway, so it's kind of harmless to think about the extra dimensions there. All right, so that's the setting. Now, an anytime you have an invariant, you should ask yourself, what's the range of values that it can take on? And there are famous conjectures about this, famous unproven conjectures about this, and I'm not about to prove them for you, because I can't. But for example, the simplest resolution in some way is the resolution of the residue class field, resolution of K as an S module. And that's the Koszul complex. You probably all know that. It works with the exterior powers of the free module on N generators. And so the betas in that case are the binomial coefficients. And if you add them up, you get 2 to the n, for instance. So the sum of the betas is 2 to the n. In that case, the betas themselves are the binomial coefficients. And one of the many famous conjectures about this is due to Horrocks on one hand and Buchsbaum and myself on the other. So just as an example of an open conjecture, the sum of the beta ij, well, let's say, let me make a hypothesis not to be too trivially wrong. If M has finite length, so think about length, if you like, or as dimension over the field, finite dimension over K, finite vector space dimension, then the sum of the beta ij's is at least 2 to the n. That's a conjecturally true. It would have some slight extension of that. You can make something more general than a free resolution. Shouldn't think that this is the end of the game. A free resolution you can think of as an upper triangular matrix with entries right along the, just above the diagonal. Namely, take the direct sum of all those modules and think of this as a map from the direct sum to itself. That's sort of silly. But you could generalize that idea by taking any matrix, maybe upper triangular, whose square is 0. That's a generalization of a free resolution. And in that context, there's a conjecture just like this, which the topologists are very fond of, and which would say something about what groups can act on spheres in an interesting way, or on wedges of spheres. So Gunnar Carlson down at Stanford, for instance, has worked on this kind of thing. His students work on it now. So there are lots of variations of this kind of thing, and it just points out the fact that we don't really know what values these invariants can take on. If you look at examples, they're pretty wayward. So I was very surprised when somebody made a conjecture that said not what values the invariants can take on, but something that seemed to be just a little bit weaker. And I thought, aha, these people are really optimistic. I'm going to find a counterexample. And after thinking about it for a while, I didn't find a counterexample. And then Frank Schreier and I proved the conjecture. And that's the group of things I want to tell you about. The people who made the conjecture were Mats Boy and his student Jonas Söderberg. Two Swedes. So this is Boy-Söderberg theory. And it describes not, unfortunately, which values the invariant can have, but rather the cone of values that they generate, that the possible invariants generate. So let's see why that's a natural idea. There's a cone of Betti tables. So this thing is the Betti table. Now, the main observation is that if you take the direct sum of two modules, then the Betti tables simply add as elements of that vector space. So whenever you have that kind of situation, you should think to yourself, aha, I have a cone. You can add. Big deal. I have a semigroup, really. But if you want to simplify a semigroup, then you can take the cone it generates. The semigroup is actually what we don't know. We do know now the cone. And the rest of my talk is going to be a description for you of that cone. And maybe something about how you investigate it. All right, so I was going to actually compute a Betty table for you. I think maybe it's worth doing that. But first let me say that m plus n, so the Betty table of that, I'll call this Betty of m, beta of n. Beta of m plus n is beta of m plus beta of n. By the way, if you have extensions, if you don't take the direct sum but some short exact sequence with an m on one end and an n on the other end, then you get a kind of sub-additivity. So that'll stay inside the cone of the things they generate. So that also adds a little interest to the cone. Sorry? Ah, yes. True. Thank you. All right. So, so there is a cone, and the question is, what is it? All right. So an example of a Betty table. Let me do it over here so we can hang on to it. The one I wanted to write down, since it's easy, how many people here have computed by hand the free resolution of something in their lives? Not everyone. Okay, so maybe you'll learn something from this. So I'm going to take m, polynomials in 3 variables, first of all, k of x, y, z. M is going to be s modulo x squared, xy, and xz squared. 2 remarks on this example. First of all, it's a cyclic module, represents a ring. And that's what the most interesting modules are. The rest of the modules are around. You better take them seriously, but they're mostly good for analyzing these modules, because we're really interested in subvarieties in projective space. That's somehow where this all comes from, or invariant theory or things like that. Anyway, so there's a nice cyclic module. And how would you resolve it? Well, the beginning is pretty clear. I'll start out with an S. Right? S certainly maps onto that. And the kernel is also clear. It's generated by x squared, xy, and xz squared. I'm going to need a little more room, so I'm just going to erase that part and write it again as m s. And here's x squared, x, what did I say? X squared, xy, and xz squared. Okay, so there's the first map. And now, in fact, I want to write it a little more cleverly. I want to write here a free module that will map onto this kernel, which is that ideal. And, of course, it should have 3 generators, 2 of them of degree 2 and 1 of degree 3. So I will write the generators of degree 2, for reasons which will be clear in a moment, down here. S of minus 2 squared plus S of minus 3. And I think of this map as x squared and xy, and this map as xz squared. Okay? So here's a map of degree 3. Here's a map of degree 2. Now, the other thing that you might notice if you thought, why did he choose that example, is that I chose an example of an ideal generated by monomials. And that's because it's really easy to compute syzygies of monomial ideals. That's one of the things that makes toric geometry always attractive to me, is that I think, I'm going to be able to compute everything. So, unfortunately, not quite true, but close. So, in particular, syzygies of monomial ideals are always the obvious syzygies, generated by the obvious syzygies. Maybe not minimally generated, but at least generated. So, what's the obvious syzygy on 2 elements? Well, you multiply one by the other, and then they get equal. Use the commutative law. So in this case, xy times x squared is the same as x squared times xy. So I can write a syzygy by putting the difference. Now, I see that's not a very good syzygy to write down, because I could have divided it by something and still gotten a syzygy. So the general rule, which was worked out as a theorem by Diana Taylor many years ago, says that works. If you always just divide by whatever you can divide by, you will get enough syzygies to generate. Easy to prove. I leave it for you as an exercise. In this case, I have s of minus 3, and here's the map with x, y, let's say, oops, I didn't divide, y and minus x, right? And what else could I do? I could take x squared and xz squared, and I could divide by x, so I get a syzygy which is x times xz squared minus z squared times x. So I have something s of minus 4 here, and here's that map. But I also have a relation between x, y, and xz squared. Again, I can divide by x. So I actually have two relations of that degree, 4. And what are they? They are, let's see. So I'm going to take this element as the first one. So I have something like z squared 0 minus x, and the columns are the relations. And to get this one, I have to take z squared and y, so 0 z squared and minus y. Okay? Very clear? Sorry? Sure, this map really goes from this free module to this free module. That's why I'm thinking of the sum of those two. And then what's the syzygy on this whole thing? Well, if I'd just taken the really stupid syzygy, it would be x squared xy and z squared. And it turns out that the same kind of argument says that I can really do that after dividing by all the things you could have divided by. And now can I get it right at this point? I want one generator here of degree minus 5, and I guess I have to multiply by x here and by, or no, I have two things there, x and y. Yeah, I'm going to multiply. I'm going to divide these by x and y. I probably wrote this down in the wrong order, but well, I'll let you get it right. This map, after a permutation of the rows and columns, is x, y, and z squared. The z squared goes here. Let's see, is that exactly right? Z squared times y is this y times this z squared. Maybe I should write it in the other order. Yx, as I've written it. Something like that. And maybe there should be some signs. Sorry? Where? Here? Here you think I have y? Oh, sign, yes. Plus or minus. Okay? Fill in the signs. Okay, so there's a free resolution. Now, why did I write it in this funny pattern? Well, a few of you know the answer. I want a notation for this kind of Betty table, which is very compact. And I can do that here. Here's my notation for this. I'll think of it as a table like that. Here's a 1 representing the rank of this free module in position. The columns are going to be the different free modules, and the rows are the different degrees. 1 here. And then I want to step down by 1. If I have a linear map, I step back straight. If I have a quadratic map, I step down by 1. So here I have a 2 and a 1, and then a 1 and a 2 and a 1. Okay, so that's the Betty table in a nice notation. Sometimes if I want to emphasize the fact that the rest of the entries are 0, I might put zeros or I might put dashes. Okay, so there's the Betty table associated to this easy example. All right. Now, how do you analyze a cone? We've got a cone to work on. How are we going to talk about it? Well, you people have been analyzing cones a lot lately, so you surely know the answer, which is you look for extremal rays. Oh, no, wait, that's not the right answer. You should look for the facets. The extremal rays of the dual. Well, you really need both, is the truth of the matter. So the idea is this. There are rather obvious extremal rays, or rays that you might hope are extremal. And I'll write them down for you. If you want to prove that they're right, how would you go about it? Well, I have a bunch of extremal rays. I see the facets from the rays. Fine. I can write down the equation that the facets should satisfy. Now, if I want to prove that everything else is really in the cone generated by those rays, if I wasn't sure that I was right about the extremal rays, then I just have to prove that the rest of the resolutions in the world are, positive under those equations. So that's both historically accurate and a kind of obvious way to proceed. That's the way the story came out. So we have to ask, what are the extremal rays? It's a sort of more refined version than this question. What are extremal rays? Now, well, there are some sort of obvious things to say. First of all, if you take the sum of two things, then the number of entries in your table can only go up, right? Because they're always positive sums. So an extremal ray had better correspond to a table with as few as possible entries, whatever that might mean. You've got to have an entry in each column of the table because there's a free module there. It had better not be 0 because once it's 0, that's the end of the resolution. It never goes on. So all the columns of the table had better be occupied. So sort of stupid, obvious guess, must be wrong, it's so stupid, is that it would be enough to have one entry in each column. Let's just look at the things with one entry in each column. That's right. Those are the extremal rays. So that was the big conjecture of Boy and Söderberg. By the way, they didn't make it in a vacuum. There was an older conjecture called the multiplicity conjecture, which I think I'm not going to state for you. It would take more time, which people had been trying to prove for about 20 years. And nobody could prove it. It looks, when you first see it, like an identity on Betty tables. And then you realize that it's unfortunately not true for all conceivable Betty tables. But the ones that it's not true for don't seem to be modules. So you have to restrict the collection of Betty tables to make it true. And this was the obvious restriction that made it true. It was known and easy for these special ones. And if these were the extremal rays, then it would be trivially true. And that, I think, was the motivation for the conjecture. Anyway, what are the extremal rays? The answer is try Betty tables with one entry per column. Now, what does that mean about the module? There's one entry in the first column. Those are the generators of the module. And to say there's just one entry says that all the generators have the same degree. Then you look at the relations, and they all have to have some given degree. And then the relations on those all have to have one given degree. So these are usually called the pure Betty tables. Pure Betty tables. And I'm going to make an additional restriction. If you're an expert in this subject, then you'll like the following statement. I want to look at pure Betty tables of Cohen-Macaulay modules. If you're not an expert, then you should say to yourself, let's stick with the case of modules which are finite dimensional over K, finite length modules. Those are completely equivalent ideas, but it would take me a while to connect them correctly. So one way or the other, pure Betty tables of, on the one hand, Cohen-Macaulay modules, that's sort of the grown-up way to think about it. Or you could think, without losing a thing, modules of finite length. And again, finite length just means finite dimensional as a vector space. Okay? So take your choice. So let's see, how are we going to do this? So to specify one of those modules, you just have to specify which row of the table that non-zero entry is going to occur in. In other words, you have to specify the degree of each syzygy. So the degree of the generators of each syzygy module. So given D0 up to D0 less than, well, you see the degrees have to go up, right? Because there have to be maps between these modules. And this is only the zero map between a free module with a generator in low degree and a free module generator in high degree, because you've got to send the generators somewhere in the same degree. And if it's zero in that degree, there's no place to send them. So the degree sequences that are possible are, or conceivable, are D0 less than D1 less than Dn integers. And they could be any integers, positive or negative. A pure module of type, let's call this whole sequence D, of type D is a, well, Cohen-Macaulay or finite length module such that beta ij is 0 for j not equal to d. D sub I, sorry. And if I want to say Cohen-Macaulay modules, then I could have sequences of arbitrary length. So I'll put an S here and not worry about the other case. But again, maybe I should stick to the finite length case, except I want to analyze that example, which is not Cohen-Macaulay. So I want to do this general way for the moment. Now, sequences of, increasing sequences of integers, that's a pretty commonly occurring object. It's called the Young lattice, the set of those things, often. And there's a natural partial order on them. There's all kinds of combinatorial structure there. Let's just pay attention to the partial order for a moment. So partial order. Well, it's the term-wise partial order, except that I have to potentially compare sequences of different lengths too. So I'll just pad everything by infinity. Term-wise, pad sequence by infinity. So in other words, if you have two sequences that have different lengths, then the shorter one is always bigger, or they're not comparable. Either it's bigger or they're not comparable. Okay, so that's the partially ordered set of pure tables. Now you've seen some of these, right? If I take a Koszul complex on a bunch of equations all of the same degree, I get a pure resolution, no problem. You've seen any more? These are not so common in the world. And so my first thought, when I first saw the conjecture, which I'll state in a moment, was there just aren't enough of these modules to make this kind of game worthwhile. Now, people had worked on modules with pure resolution before, and if you think about it, there's a kind of obvious restriction. Let's stick with the modules of finite length, then, and ask, what could you say about the Betti table just knowing the degrees? Could you say anything about it? Could the Betti numbers be just independent functions? Well, a module of finite length has Hilbert function equal to eventually 0, right? High degrees at 0. So the Hilbert polynomial is 0. The coefficients of the Hilbert polynomial are all 0. How many of them are there? Well, the Hilbert polynomial of a module over our polynomial ring potentially is a function of degree n minus 1. Is that right? Let's see. One variable, the Hilbert function is constant. That's degree 0. So n minus 1. How many coefficients does a polynomial of degree n minus 1 have? Has n coefficients. And if you look at it, those coefficients are actually linear combinations of the beta ij's, if you just write it down. Linear combinations. So to say that you have a module of finite length tells you that n linear functions vanish on the Betti table. of course, the functions depend on the degrees. N linear functions, and you have n plus 1 numbers to determine. So if the equations are independent, you'll have a single ray of possible solutions. If they're dependent, then you might have more. And the first remark that Boy and Söderberg made was that these are always independent functions. It's a kind of van der Waals situation. And so for any pure type like this, there is a unique ray of possible Betti tables. So a proposition, and I've just told you the proof, for any D, there exists unique type of possible Betti tables. Exists a unique possible Betti tables is what I wrote, but what I meant is unique ray. Because, of course, once you have a Betti table with beta ij's, you can always get twice it by just taking m plus m. Right? That has to make sense and has to satisfy whatever restrictions there are. So let's do a little example. In fact, it's easy to work out the numbers explicitly. Let me write them down for you. So a better proposition, proposition prime, if M is pure type D, then beta I d sub I of M, that's the only beta ij which is non-zero, is actually equal to some multiple, R, the same for all the i's, of the product of 1 over dj minus di. You better take j different than I to make that right, make that possible, and I better take an absolute value sign there to make it positive. So that's pretty simple combinatorial thing. If you think about it, you shouldn't be too surprised. That's the kind of van der Waals. That's a solution to the van der Waals equations, right? Looks like that often. So that tells us the answer. So if we're going to have Betti tables that are pure, we better have Betti tables with those numbers in them. So let's try an example and see whether we could possibly do that. What's the simplest case? Of course, let's take 3 variables again. Simplest case would be 0, 1, 2, 3, right? That's a plausible sequence of D's. And you know the answer. That's the Kazul complex. That's the resolution of the residue class field. All the generators, the one generator has degree 0. There are 3 generators of the first syzygies, etc. So let's take the next case. So I guess the next case would be 0, 1, 3, 4. So there's D. Okay? What should we have? Well, what are these funny numbers? In the 0th place, I'm going to get 1 over 1 minus 0 times 3 minus 0 times 4 minus 0. That's 12. So I get a 12th. So the Betti table looks like 1/12. And then in place 1, I have the difference, the product of those differences, which are 1 times 2 times 3, which is a 6th. And that goes here. And then in this place, I have 1 times 2 times 3, the same as before, a 6. But now I've jumped 2 degrees, so I go down 1 in the Betti table. I have a 1/6 here. And then in this place, I have 1 times 3 times 4, a 12th again, 1/12. So there's the Betti table. Of course, you know perfectly well that's not a Betti table because there aren't integers. So let's just multiply and make them integers. 12 I have to multiply by. So I multiply 12 times this, and I get 1, 2, 2, 1. Is there a module with that Betti table? We ask ourselves. Some of you know the answer probably for a long time already. Think about it for a moment. Could there be such a module? What does this Betti table mean? means I have a cyclic module. It's the ring mod an ideal. What's the ideal generated by? It's generated by two linear forms, right? And then the two linear forms have two relations on them, which happen to be quadratic. That doesn't sound so good. If I have two linear forms, it's x and y, right? That's what linear forms are. And the relation on x and y is y times x equals x times y. So to have a resolution there would have to be a 1 there. This does not exist. Just does not exist, right? End of conjecture. Well, not quite, because the conjecture should have been just about the rays. This is the difference between knowing the semigroup and knowing the cone. What if I multiply this by 2, by 3, by 7? Might I get modules then? Well, we don't know those modules so well. It's not so easy. However, when I was a young man, I worked with David Buchsbaum a lot and learned about this resolution. If I multiply by 2, 2, 4, 4, 2, I get what is in fact the resolution of the generic 2 by 4 matrix. Generic 2 by 4 matrix of linear forms has that resolution. That's because of Cramer's rule. Cramer's rule says that you get the kernel of a sufficiently generic matrix by looking at the minors of the matrix, and those have degree 2. And there are 4 of them because, sorry, there are 6 of them. Here was a 4 by 4 matrix to fill up, but if we made it skew symmetric, then it would have just the right number of entries, and that's what happens. 3 plus 2 plus 1 is 6. So this exists. This is the resolution of the generic matrix. Well, we shouldn't stop there. Which multiples actually are honest modules? What if I multiply by 3? 3, 6, 6, 3. Does that exist? That's one that I actually don't know how to write down by a formula, although I guess I could with a little effort. But it does exist, and there's even an equivariant module of that type. And of course, once you have 2 times the basic thing and 3 times the basic thing, then you get n times the basic thing for every n bigger than 2. So there are modules there, but it's a fight to get them. It's a struggle, right? So that's more or less what one knew at the time Boy and Söderberg made their conjecture. And what they conjectured was the following theorem now. So this was the Boy-Söderberg conjecture, and it was proved by Frank Schreier and me. And then Boy and Söderberg noticed that our proof actually proved more, and so they made a bigger conjecture, which was also handled by our proof. And so there are actually 2 Boy-Söderberg papers that I'll include in this. Anyway, after the fact, the theorem is this. 1, there exists pure modules with every degree sequence. So that means, of course, somewhere on the ray. Doesn't mean you start out. Second, every Betti table can be decomposed as a sum of these in a positive way. That is to say, every Betti table is a positive rational linear combination of these pure Betti tables. You now know the pure Betti tables because you just, this is a pure Betti table. This is what they are. That's all. So every module is a rational linear combination. Let me state it as that as part 2. Every Betti table is a positive rational linear combination of pure ones. So far, I don't really have any excuse for giving this talk in this venue because fans and things haven't appeared. But actually, there is a fan lurking. And one way to let it appear is to say what is really a more refined version of number 2, which is that this expression in 2 is unique if you insist that the pure Betty tables you work with for a given module occur in a totally ordered sequence. I'll unpack that statement for you in a moment. The expression of 2 is unique if, well, there is a unique expression of this form with totally ordered pure tables, pure sequences. Not so clear what things you should think are totally ordered. Let me think the pure types are totally ordered by this term-wise order. So what is this 3? How should you interpret it? You have a cone with all these rays going out. I'm claiming you can express any point in the cone uniquely as a linear combination of certain subsets of the cone. Well, those subsets must be bases for the space, right? You can't have linear dependence relations. So what I'm describing is a simplicial fan. This statement is equivalent to saying that this cone is really a simplicial fan where the rays are the pure resolutions. So for this group, that might be even a better statement. So equivalently, the cone of Betty tables is a simplicial fan generated by the pure rays an equivalent statement. There's a third statement which makes this whole situation attractive too, which is the greedy algorithm works. You want to decompose a Betty table? Do it in the obvious way. It's sure to work. So let me tell you what the obvious way is for the example up above. So let's decompose that Betty table, which came from this messy resolution, which we no longer need, in the greedy manner. So I want a totally ordered sequence of degree sequences, so I better start with the smallest degrees that occur. Otherwise, I'm really up a creek. Right? I'll never get anything else. So I start with the degree sequence 0, 2, 3, 5. Okay? So the degree sequence I start with is D is 0, 2, 3, 5. And we could play the formula. Since arithmetic in public is not my strong suit, and it's not much fun to watch anyway, although this one I know, actually I don't have to look at this. This one corresponds to the Betty table 1, 5, 5, 1. Those are the Betty numbers. Why do I know that? That's the Betty table of 5 points in P3. We look at the homogeneous coordinate ring of 5 points in P3. That's what it looks like, and this occurs in other places too. Actually, any such resolution of a Cohen-Macaulay module has a skew-symmetric matrix in the middle, and the generators of the ideal are the Pfaffians, the 4x4 Pfaffians of that 5x5 skew-symmetric matrix. If you know a bunch of linear algebra, that will make sense to you. It's a theorem that Buxbaum and I proved many years ago. So that's the first component. So let's subtract. What does the greedy algorithm do? It says, take as much as you can in your mouth using that, right? That's greed. So how much can I take? Well, I better leave something positive, otherwise it won't look like a Betty table anymore. So I subtract the biggest multiple of this from this, which leaves it positive. Now what is that? Looks like the critical one is this 1 here. I can only take away a fifth of this. So I'll start with 1/5 of that. And now I want to add something more, and I'm just going to write down the result because time is so short, as always. So it's this plus 1/10 of 3, 10, 15, 8. Ever see that module before? I never had either. plus 1/6 of 1, 4, 3. These are cubics. That one I've seen before. That's the Betti table of 6 general points in the plane. That's a very familiar example. Plus 1/3 of 1, 1, a single cubic. So there, if you add that up, I hope it comes out to the right thing. It did when I last added it up, but these things change with time, so you might want to check. Anyway, that's a sort of typical decomposition. As I said, this is not going to pin down for us what Betti tables are really possible. All it gives is, give me a Betti table and I'll tell you whether some multiple of it is possible. That I can tell you now for sure, but I can't tell you which ones are possible. However, it's not completely hopeless, and you can get more information than you might think at first. For example, about this conjecture, right? This is a typical conjecture which you can't hope to prove by using the Bois-Söderberg theory. Because if I take a multiple of a given table, of course it satisfies this, right? So there's sort of no information there. Nevertheless, there is information, and Daniel Ehrman, whom you've all gotten to know, has used this, for example, to prove a weak form of this. I've just stated quickly. If you assume that the Betti table looks like this, something here and then something down here, and only the lower half of the diagram that you drew and zeros up there, then it satisfies this, and even a somewhat stronger form of that conjecture satisfies this conjecture. This is Daniel Ehrman. So if you work hard and are clever, then you can get quite a bit of information about specific Betti tables, even though you really can't hope to say everything using this tool. It's very interesting to ask which Betti tables do occur and what kind of modules they occur for, and whether this decomposition has any meaning in terms of modules. Those are very interesting and very open questions. What kind of meaning could it have? Well, here's a possibility. No one knows how to prove the following is false, which is as close as I'm going to come to saying that it's a conjecture. Suppose I take a module and I look at its Betti table. Well, it probably has no relation whatever to the pure tables that I write down in the decomposition. For instance, here, it's pretty clear that this module is not really made up of a fifth of this one. What would that mean? However, let's say I multiply this module by, well, let's see, 60, or maybe 120 for good measure, or 1,200, right? Then maybe there's a filtration which has, as its factors, modules with these pure tables. Could be true. That would be nice. I would love to see a theorem of that kind, but I don't know how to do it. Since I'm going to run out of time before I get very much further, in fact, maybe I won't get any further and just state another conjecture or two. You might ask, what is this? How about other toric varieties, right? We've spent a whole hour talking about one toric variety, projective space. Well, there are others. You've been learning about that all week, and they're not so different. If I take another toric variety and I take a sheaf, well, roughly speaking, it comes from a module, right? You did that. Ah, good. And the module is graded. It has a sort of funny grading, but okay, it's a grading. And there's some fancy ideal floating around as well. Now, you could think about that resolution. You could think about it in terms of sheaves, of course, but you could just take that as a module and resolve it. You get a graded module with a graded resolution for a different grading. What are they? What are the possibilities? There's another cone. Is there a theorem like this? Could you prove it? Nobody knows how to even guess it. Even for P1 cross P1, the next simplest toric variety, no one has made a conjecture yet. The field is open. And even for the weighted projective space case, no one has made a conjecture yet. Right. There are kind of obstructions. You might say, well, okay, let's just conjecture the same, pure, right? Everything has just one grading in each degree. That can't be right, as you can see pretty quickly from thinking a moment about it. But there is some minimal set of rays. I mean, cones have extremal rays, unless they're much more complicated than this one is. So what is the answer? Well, it's, of course, a subcone of this one in some sense, except you've changed the grading. It doesn't seem that hopeless, but nobody knows. So there's that kind of question. That's related to the question of what kind of equivariance could you get. For instance, could you hope to have a module which was equivariant with respect to the whole torus action and not just with respect to the single grading? Answer, yes, at least in characteristic 0, and I guess in all characteristics, so I haven't written it down carefully. In fact, there are pure modules along these rays which have GLN actions. There are GLN equivariant modules that have these resolutions in characteristic 0. At least we don't know in characteristic P. So there's that kind of question. That's closely related to the toric question, too. Even the simplest, stupidest graded case, well, let me say the first one I can't touch, one of the many ones I can't touch. We've stated 2 already. You could have weighted projective space. You could have P1 cross P1. Or how about the one where you look at the whole Zn grading? What Zn graded resolutions are there? Well, you know, these are not Zn graded. You have many different, you can make them monomial in some sense. You can make them Gm to the n graded, but these will have many different fine degrees. Well, what's possible? Just say what's possible. Nobody has a guess at the moment. Sorry? I do not know. I do not know. I guess so, but I don't have any real reason for making that guess. I think this is a good time for me to stop.